Good evening, and though this is lecture 4, we're going to finish first the reminder of lecture 3. So, okay, hopefully everything is okay. Recording, hopefully okay. All right. So, where we left it last time was we were about to introduce these diagrams, right? So, they represent very interestingly the relationship between languages and the process of compilation or interpretation, right? So, last time we learned essentially two processes, two ways of processing a programming language. One was interpretation, and that was the dynamic semantics that we're talking about. And now, with the definition of the virtual machine, we essentially introduce compilation, right? So we know how to compile the expression language that we had into a very simple virtual machine that we have just defined. All right. But that virtual machine was sufficient for the purpose at hand, which was evaluating a simple expression. So we're going to have these diagrams. They're called T diagrams. All right. And we're going to represent as a square box with these two inscriptions, let's call them, right? Two pieces of text in one that is above and the other one that is below, right? Representing the fact that we have a language and it is implemented into another language, right? We had the language EPL, right? And we implemented the interpreter in Java, right? So the square box represents interpretation essentially, right? And then we conjoin that with a T piece, right? Think of this as a Lego, and each piece is a separate object, right? A separate entity. So we have a translator from Java to the JVM bytecode written in essentially C++, but it's a binary, right? So it executes, it is written in the language x86. So this T represents a compiler, right? This T represents a compiler. Takes a Java program, turns it into a JVM bytecode, and it runs on x86. It's an x86 binary. Actually, if you want to be pedantic here, I'm going to say it's an x86_64, right? Because nobody uses 32-bit machines anymore. So that's what it would be. The arrow-shaped element at the bottom, all right, represents the hardware. So the x86 binary runs on an x86 piece of hardware that can understand that binary. But notice that the hardware is nothing else but an interpreter. But instead of being software, it's just made of hardware, right? Does nothing else but interprets the binary opcodes inside there. So the result of that, all right, is an EPL, is the same EPL program that now runs on JVM, right? So we have written an EPL interpreter in Java, and the result of that we have that the EPL essentially runs on top of the JVM. Does that make sense? So this thing, written from left to right, essentially expresses a process of translation. Right? The T that is there, remember it's compilation. Compilation is the same as translation. So you can use this mnemonic. T means translation. right? Not everything is ever compiled. Some stuff is exclusively interpreted. So let's do something else, right? Now we have a, let's say a file that we can call bill. So we introduce a new kind of element. We just don't have just a language. We have a specific instance of that language, bill, right? So the bill, we call the file, is written in the language EPL. The EPL language is interpreted on top of the JVM. It's this box right here. So this box. So essentially, as a result of this, we were able to produce this box. Okay? And this is the box that we have right here. It's the box that we have produced. Right? Now, the JVM executes on top of the x86. That is given by the Java framework. Right? So, what implements that? What is this box represented by? What command do you run to have this? Right. So which command is that? Java, right? Just Java. How about this one, the T here? Wait, that's Java C, right? So it's a given, right? So in this entire picture, we started with this box. This was written by us, right? And everything else was given, and this was the product of the whole process, right? This box we can actually plug in here, right? So we have a file written in EPL, in the language EPL, right? This is our box, takes EPL and interprets it on top of the JVM. But the JVM bytecode is not directly executed, right? It is further interpreted by the JVM, right? Which sits here, right? The JVM runs on top of x86, and then x86 is a piece of hardware, so we represent that as this arrow-shaped pentagon. Does that make sense? So we can express these processes of execution, of translation and interpretation with these T diagrams, right? The same stands for OCaml, right? So let's say that we, instead of implementing our EPL in Java, we implement the EPL in OCaml. Now OCaml may or may not have a virtual machine, right? So if you look very carefully inside the OCaml framework, there's a compiler that compiles to OCaml bytecode, and there's another compiler that compiles directly to binary. And there's advantages and disadvantages to both, and we can delve into that later, right? But let's say that in this case we're using the OCaml compiler that goes to binary. So from OCaml, right, we produce x86 binary, right? But that compiler runs on top of x86, right? So it's made of x86. It's an x86 binary itself. It is a binary, right? And then this executes on top of hardware, and the result of this is that from that EPL gets executed on an x86 as an x86 binary, right? So the interpreter of EPL is an x86 binary, right? We take the OCaml code that represents the EPL interpreter, compile it, we get an EPL interpreter that is a x86 binary. Okay? Now we take that and given some file that is an EPL program, right? We take this box, we plug it in here, right? And we use it, right, running on top of x86 hardware to essentially evaluate the expression. All right? So what happens, what's the difference between these two, right? So these two steps are collapsed into one in the case of OCaml, right? and it would be collapsed into one in the case of a lot of languages, right? C produces a binary. What else of the old languages? Pascal, maybe some of you have used Delphi, right? So produces a binary, compiles to an executable, right? So automatically these two steps are essentially collapsed. Okay, and this is what you're seeing on this slide, right? So the two boxes here are collapsed into one, and also the T here is shorter, right? Because if we go here, no, the T is the same, sorry. The T is the same. All right, and how about using our own virtual machine, right? Which we called EVML, right? So we take EPL and we have written a compiler, right? EPL into EVML, and that compiler, let's say we write it in OCaml. You would have one lab on that, right? So that is written in OCaml, right? So now we have an OCaml compiler, which is the T here. So notice how we place the, so first of all, this is a T, right? It's no longer a box because it's a translator. It's a compiler. Previously we were writing interpreters. So our EPL to virtual machine is now a compiler. Takes the EPL, produces our own virtual machine code, right? And that's a program called OCaml, and this box has to be, this element has to be represented by a T, right? The OCaml that we have, in which we have written our compiler, has to be fair compiled, right? Has to be fair compiled. So OCaml is translated into x86, right, by running on top of an x86. The compiler itself is a binary. And being a binary, it runs on a piece of hardware, which is here, right? The x86 binary, all right, can now be used. So what have we produced, right? The x86 binary that we have produced can be used to translate EPL into EVML as a binary, right? So the distinction is that we can run this, but we cannot run this. Why? Because we don't have an entity that executes OCaml code directly, right? OCaml code has to be compiled and then executed. So meaning that if I have to compile it, I have to get here. Is that clear? But because I have an executable, and then what's missing here is on the right side I should have an execution, right? Where I take an eBill and I use the EVML actually I might have that. I might have that. All right, so what I should have here, I hope I fixed. I should have something like this. Okay, so this bubble thingy, and this is Bill, and here we have EPL, and then I would have this box, and I'm just gonna say that this goes here. And what do I get here? I get Bill, and what do I write here? EVML, very good. Right? So this object that we have produced, this binary that we have produced, can be used to take a file written in the EPL language and produce a binary which, when executed, will give me the evaluation of the expression written inside of the of this file. This file will be something like 2 plus 3, right? Because our language currently is a language of expressions. So we're expecting that this binary, when executed, will just print out 5, right? Does this make sense? Now, it's important to remember the distinction between interpretation and compilation. Okay, wonderful. So, so far we obtained actually I was wrong. Scratch what I said previously, right? So this is a compiler from EPL to EVML, right? So the problem is I cannot execute. I wasn't completely wrong, sorry. The problem is that I can't execute that, right? So I have the two bubbles. So I represented it like this, right? This mushroom here, I cannot actually execute it. So this is indeed bill to EVML, but EVML is something I can't execute, right? What can I execute? What can I execute? Only this, right? This is the only thing I can execute. So I still don't have, so I have something that is useful, but I'm not done with it, right? And I've done the wrong thing now. All right. So once I have the build to EVML translator, right? I have to get to execute that, right? So I need a either a compiler or an interpreter for EVML, right? So let's say we write a interpreter for EVML. So we write essentially, this would be what a virtual machine looks like, right? So a virtual machine is an interpreter for the bytecode. All right, so we take the EVML, we write that in OCaml, and then we put it through the OCaml translator, and we get an EVML that can execute on x86. All right, so then finally, we would have something like this. Right, so we have this box, and we have the T from the previous one, right? So I would start with a box. This is bill, and this is EPL, right? I have an EPL that I have a compiler that takes EPL into EVML, right? And this was on x86. This was on the previous slide, right? And here I can put the hardware, right? What I get here is a bill EVML, right? This is a mushroom. And then I can take this mushroom and I can use the EVML to x86, and then I can use the hardware. Okay, so now everything comes together. So this thing should have been on this slide. Okay, and the two previous slides, they are combined in this one. Okay, cool. So remember, a typical exam question is, I'm going to give you a sequence of operations on languages other than the ones that you're seeing in the course, right? So we're going to take, for instance, a React program that is translated by the Babel. Are you familiar with web technologies? Goes through something like Babel, becomes regular JavaScript, goes into the browser, right, where there are some hooks, but it still has, I don't know, other elements in it for which there are hooks in the browser. And I wanted to describe the entire process of translation in terms of T diagrams. So yeah, try to keep that in mind. It's one of the usually simpler problems, and it's important that you understand these diagrams and the relationship between compiling and interpretation. One thing I forgot to say, right? We typically represent or say that virtual machines are interpreted, right? Virtual machines are interpreters for their bytecode. And we're saying that, you know, a binary like Java essentially takes the Java bytecode and interprets it, right? That doesn't always happen. There's a new technology, actually it's not so new, but there's a kind of technology that differs from this and works more like a compiler. Do you know what it is? Louder, please.
Is it JIT?
Yes, just-in-time compilation, right? So what happens is that the bytecode is loaded, then it is analyzed dynamically, right? So the virtual machine places hooks into the bytecode and sees how frequently it executes certain parts of the code, right? And those parts that are executed very frequently, after a few minutes of running, the virtual machine stops, compiles those parts into real binary, and then goes and executes the binary every time, right? And that speeds up the code a lot. So this is why it is very confusing. So a lot of people say that Java is slow, but on the other hand, a lot of people say that Java is very fast. So Java is comparable as performance with C++. And this is why they say that, right? And they have different experiences, because if you run relatively small Java programs, then you're not gonna, the compiler, the virtual machine is not gonna have enough time to analyze the bytecode and figure out and get to the point of performing just-in-time compilation, right? But if you have programs that run for a few minutes, which, you know, in order to run for a few minutes nowadays, you need to crunch quite a bit of data, right? So when I'm saying run for a few minutes, actually accumulate a few minutes of CPU time, which, if you remember from your operating system class, is not that easy, right? Most programs, even though they sit in front of you for hours, most of the time they're waiting for input-output, and they don't consume CPU cycles. So if a program gets to that point of accumulating a few minutes of CPU time, then the virtual machine comes into play, the just-in-time compilation comes into play, right? Stops the virtual machine, performs the translation into binary, and then the program becomes significantly faster. All right. So you know, so there's these discussions on Stack Overflow very, very frequently. And again, I've hit the wrong thing. All right. Any questions so far? So you have this sequence of commands, And one exercise is to draw the T diagrams for it, right? And an exam question might look like that. Are we all fine? Everybody's happy? Cool. Big step semantics for EPL. So we've looked at how we interpret the code, and so trouble is that because the language is so simple, pretty much all the ways of all the types of semantics look very similar to one another. But as we're going to add more operations to the language, then we will be able to differentiate a little bit better. So we're gonna present this as a new type of semantics. We're calling it the big step semantics. It will be easier to understand why it is called big step once we have a simple iteration in our language. We're starting with the notion of contraction, right? Which is very similar to what the primary operations were doing before, right? So essentially, we evaluate a simple expression to its value. Something like 2 plus 3 becomes 5, and we consider that to be a primitive, or 1 plus 1 to be 2. Okay? So, right, so the thing that we allow here, because previously we were going after a step-by-step evaluation, but we were doing it in a way that was going from smaller expressions to larger expressions, right? So now what we want to express is the phases through which the expression goes as it gets evaluated, right? This is very similar to perhaps the way you were taught to evaluate an expression, right? When you were taught to do that in elementary school, you would have to copy most of its expression and only evaluate one operator, right? So this is what we want to capture. We start with a very long expression, and the next step is that we have contracted one small operator, and we have still a relatively long expression. And then we move on and we contract another small operation, and we still have a relatively long expression, right? And we keep doing it until we have one value, right? This is not what we were doing in the previous type of semantics, where we would say what? So I'm trying to remind you. Okay. So previously, let's say our final goal would be to evaluate 2 plus 3 times 5, right? And we would say, 3 times 5, so I start from nothing, right? And 3 times 5 evaluates to 15, right? And then 2 plus, and it evaluates to what's there, 17, right? So we'll have this tree where our final expression, you never see the final expression, right? This would be my final goal, but in this entire evaluation, in this entire derivation, because that's actually the term, the correct term, we would never see this big expression, right? So I would like now to see that, when I start from, let's say I want to evaluate 2 times 3 plus 4 times 5, right? So instead of taking small bits of the expression and coming up with the final result, I want to start with this and say that the arrow leads to 6 plus 4 times 5, and then the arrow leads to, and this horizontal arrow is actually this vertical arrow here is the horizontal arrow here, right? I have 6 plus 20, and then finally I have 26, right? So in this, I actually do start and I do see the expression that I want to actually evaluate. Whereas in this format, I don't. Does that make sense? Yes? Mathematically, they're very distinct. They're very different, right? No? Let me find the slide. Okay, this one is a bit has a less stuff on it, so it's easier to see what we're drawing. So let's say that my final objective is 2 times 3 plus 4 times 5, right? The first semantics that we introduced, which was the dynamic semantics, right? What do we do? What's our semantics? So we're saying that 2 times 3 goes to 6, and this is the rule, right? 2 times 3 goes to 6. On the other hand, starting again from nothing, we can say as a primitive rule that 4 times 5 goes to 20, right? Then I have a 6 here, I have a 20 here, right? So then I can say that 6 plus 20, arrow 26. So this expression that was my objective, right? You never see it quite in the semantics, right? It's sort of an evaluation that goes like a tree, and you're not seeing the transitions that appear inside the expression. So at all points, what we have is we're looking for contractions inside, right? But our evaluation is more like a tree. Whereas in the big step semantics that we want to introduce now, we're going to start from or we're going to write the following, and this is actually is going to be as a sequence. So let's draw a line here. So I'm going to start 2 plus 3, 2 times 3 plus 4 times 5, arrow 6 plus 4 times 5, right? So this is an instance of the rule. I can draw the rule here, right? 4 times 5, right? And then there's another arrow, and I can see 6 plus 20, right? And then you can look at this part as being an instance of a rule, right? And then you can do 26, and you can look at this part being an instance of a rule. Okay? So essentially, what happens here, it's a lot clearer what's my objective. I want to evaluate exactly this expression. And it's clearer that the result of this expression is the final value produced by the semantics. Okay? So how do we go about doing that? All right? So if you have a so we're going to define one-step evaluation, right? A one-step evaluation. So a contraction is a one-step evaluation. This is what we have here, right? And then if I have a one-step evaluation, then a unary operator applied to the left-hand side can be transformed into that unary operator applied to the right-hand side. Okay? So, for instance, minus 3 plus 4 can become minus 7. Right? Why is that? Because 3 plus 4 can go to 7. Right? So this is a contraction. This is a contraction, right? So I can say 3 plus 4 greater than 7. Because 3 plus 4 greater than 7, then I can say 3 plus 4 arrow 7. Because I can say 3 plus 4 arrow 7, I can say minus 3 plus 4 arrow minus 7. This is what this rule is saying. Okay? Similarly for binary operators, which are represented here, right? So here, I can perform the operation either on the left hand operand or on the right hand operand. Right? So, and this makes it very clear that the order of operations actually is not important for expressions. So if I have 2 times 3 plus 4 times 5, the first rule allows me to write arrow 6 plus 4 times 5, and the second one will allow me to write 2 times 3 plus 20. Right? So the order of the operations is not really important. Now, what do we want for the semantics? We want the transitive and reflexive closure of this, as we've seen before, right? So the big step semantics, right, looks at the entire thing that we want to process always, and shows that entire thing as transitioning through the steps of evaluation or processing that we have. Whereas small step semantics, which is what the dynamic semantics is also called, looks at small components and the way they combine together. All right? And typically they lead to the same thing, right? But in different ways, and they expose different aspects of the processing. All right? So, for instance, the big step semantics is a lot more useful when we go to programming languages, a lot more useful for program analysis. The small step semantics is the one that is useful for writing an interpreter. Okay? It is, with both, it is possible to prove that the final state of a program is what it is. Right? So they will give you the same final state of the program. But we're not always interested in the final state of the program. We're also often interested in all the intermediate states that a program goes through, right? Because that's how we understand program behavior. Does that make sense? Cool. Right, so what we want and what the actual big step semantic is the transitive and reflexive closure of the one-step evaluation, and this is what we get here. This is the formal definition. Excuse me. Okay, questions? Everybody's happy? So the important thing in a big step evaluation is that what we see is the final outcome. We see the same value. right? What allows us to write, for instance, so what allows us to write 3? So let's say I have an even more complicated expression, right? 2 times 3. Let's go the same way. Plus 4 times 5 plus 6 divided by 2. So we don't have very large numbers, right? So what allows me to write that this goes to, let's say, 2 plus 3 plus 20 plus 6 divided by 2. Right? So what do I write above here? So let's say this is the line, that the horizontal line represented by the rule, which I wasn't able to draw very straight. But what should I write? I should write 4 times 5 arrow 20. You might think, is that enough? No, it's not enough, right? What should I write? Louder. So, no. Why 2 times 3 or arrow 6? Two times 3. Sorry, 2 times. But why do I write 2 times 3 arrow 5 arrow 6? So what I need to write. So remember that we have this is a complex operation, right? So we have binary operators there, right? So this plus is a plus between what and what? Louder. What do you mean expression and value? What do you mean by that? Right, so is this plus between 4 times 5 and 6 divided by 2? No, it is between what and what? Very good. So it was between this guy and this guy, right? Because plus associates to the left. Right? We don't, so if plus is a binary operator, plus always needs to be between, all pluses need to have two sides, right? So this plus is, which are the 2 sides? If you're going to tell me that the 2 sides are 4 times 5 and 6 divided by 2, then I'm going to go and ask you, what are the 2 sides of this plus? Because at that point, that plus doesn't have 2 sides anymore, right? Does that make sense? So your syntax tree for this is going to be plus division 6, 2 plus star 2, 3, right, and star 4, 5, right? Right? So this plus is between this entire expression. Think of it as having brackets around here and whatever is on the right side, right? So then what do I need to make this a valid arrow? What do I need to write here? I need to write 2 times 3 plus 4 plus 4 times 5 arrow 2 times 3 plus 20, right? That's what I should write in order to make it valid. Does it make sense? But you see, this is not a primitive thing, so I have to draw another line here and write another thing on top of that line. Right? What do I write here? So here it's easy. Now I can write 4 times 5, 20, right? And what do I write above? I write 4 times 5 greater 20. And what do I write above here? Nothing, because it's a primitive rule, right? The greater than is a contraction and doesn't need to have anything above. Does it make sense? So our semantics, right, big step as it may be, it needs to be based on a decomposition of the expressions, right? So if you think of the evolution of the evaluation, I'm going to go to the to this page again, the page that doesn't have much on it. Okay, so how is this going to look? It's going to look something like this. I'm going to have a long expression, arrow, another relatively long expression, right? But in order to justify this transition, what I'm going to do is I'm going to have a chunk of this chunk and this chunk need to be here, right? And then I'm going to take another chunk from here, another chunk from here, and I'm going to put them here. And so on, right? Until I get to a contraction and there's nothing. Then I'm going to have another arrow. Okay? And this will produce a new piece here. But if I look at these two guys, now I have to draw a line, and I'm going to try to draw it because it overlaps a little bit. I'm going to have to draw a line above these two and then build a proof here, right? So it's gonna it's gonna look more like this. Pyramid goes to pyramid goes to pyramid. All right. Whereas the other semantics, the dynamic semantics, was more like a tree, right? It will start from an expression here and it will build something like this, right? So there's one line, then there's 2 lines, then there's 4 lines, all right? And it sort of builds up like a tree. Okay? So what we have not defined is this relationship between this arrow between the pyramids. And this is the slide that we were looking at just as I started to explain this. So let's go back there. Okay? So this is what is trying to explain exactly the relationship between the creation of the pyramids. Right? So if you have a multi-step evaluation from E to V1 and you have a, let's say, primitive operation, right, that contracts to V2, all right, essentially, right, this is what the transitive and transitive closure is, right? If you have E evaluates to V1 and then what you're left with is P applied to V1 and that you know that it evaluates to V2, then you can say that P applied to E evaluates directly to V2, right? So this is transitivity. But it's a restricted form of transitivity because we want always to have the last operation here. If E1 evaluates to V1 and E2 evaluates to V2, right, and whatever is left is P, V1, V2, and we know that that contracts to V, then we can say that P, so binary operator applied to E1 and E2 evaluates to V. Okay? So that is essentially basic transitive closure. Cool? And this is the big step evaluation. So that's the big step semantics. All right. We're going to come back to this and go in a bit more detail with the next language, which is called simple, and which actually has, I think, it has statements. I can't remember whether it has a while loop, but it does have statements. We'll see. Cool? Everybody's happy? Okay. So let's move on to the next set of slides. The language simple, and we're going to go through the same cycle: dynamic semantics, static semantics, and we're going to differentiate between big step, small step. We're going to define new operations for the virtual machine. We're going to compile it, and we're going to explain how to implement the virtual machine in a generic programming language, such as OCaml. So we're going to be a bit simplified yet again, all right? So we're going to assume some preprocessing is going on, right? Because we don't want to reduce the generality of the code, but yet when we discuss about concepts, we don't want to overcomplicate things. So what we want to have this time is built-in conditionals, right? So an if statement, function definition and application, and you're going to say, whoa, but you're going to see that this actually is not too difficult, and it's actually simpler than a while loop. And then how do we perform repetition? By means of recursive functions. So we're going to have recursive function definitions. So this language allows us to essentially step into the real world. Okay? Yeah. Our language is going to be typed. So one immediate addition is going to be types that are used to annotate our expressions. So we're going to discuss the language of types. First, we're going to have only two types, int and bool. And we can compose two primitive types, int and bool. So no strings. And we're going to be able to compose types via the arrow that represents a function from one type to another. This follows very closely the syntax of OCaml. All right, and unfortunately it doesn't. So here there's a very clear separation between functional languages, OCaml and Haskell, and the rest of the programming languages that are also typed, such as C, Java, Pascal, and so on. The language of types is a lot richer. So what we're going to have here, this in the real world, you're going to have restrictions. So you're going to have to essentially reduce your expectations. You're going to understand the limitations of Java. Let's put it this way. So we can define types in OCaml. We can implement types in OCaml in the following way, right? So we're going to have a type in OCaml that denotes types of our language, right? Seems there's a lot of recursive reasoning here. It's not really. We need a data structure to represent a syntactic component of the language, which is types, right? Every syntactic component is going to have its own type. In OCaml, this is the one for simple types. All right. Expressions are, so part of our language is expressions, and they are very similar to the expressions that we've seen in EPL, with one notable exception, which is, what do you think? So if we have functions, what do we necessarily need in our language that we didn't have before? Louder.
One type arrow, another type.
How would I have a constant of that? I mean, actually, it's possible, but so think that the language that we had only had constants, right? Had all the numbers and the true and false, right? In a real programming language, when you write your expressions, what are going to be losing?
Variable.
Yes, variables, right? So this x that you see here is variables, right? Everything else stays the same. But now, right, so we're saying that if E1 and E2 are expressions, then P binary operator applied to E1 and E2 is also an expression, right? And then, since a variable is an expression, we have expressions that may contain variables. All right. We're going to have conditional expressions that are more similar to question mark colon, right? And would be following the conditional expression in OCaml, right? So meaning that this has a value. We're saying that if E is true, then the value of the entire expression is E1, otherwise it's E2, right? So the if statement has a value. I can say 3 plus if true, then 4 else 5. That's a valid expression, right? And then we have function application, and the syntax is again similar to OCaml, which is curried. It's a curried language. This word comes from this name. It is not the spice. All right. So this guy was a logician. His name was Haskell Curry. Haskell became the name of the Haskell language. The notion of currying means a syntax for functions, right? In math, you used to write a function applied to arguments, x and y, right? And you used to open a bracket and say x comma y. Curry said, no, this is not a very good syntax. Let's use f, x, y inside a bracket. Meaning that there's an invisible operator in here. They treat this space as an invisible operator that associates to the left. And I have that f is applied to x, returns another function that is further applied to y to yield the result. Does it make sense? And it's going to introduce the concept of partial application, which we'll have to deal with. Obviously, this syntax among functional programmers became known as uncurried. All right? Currying and uncurrying are transformations that are standard in functional programming, right? Because in fact, if you look at this syntax, you can think of f. You can put a little space here, right? And you can think of f as being applied to what? To a tuple. Very good, right? So instead of having f applied to x and further applied to y, we can have f applied to the tuple of x and y, right? Conversions between the two formats are very simple, very easy to do. And typically, you will have in most functional programming languages a higher order function which is called curry, which takes this kind of f and gives you this kind of, which takes this kind of f and gives you this kind of f. And you would have another one called uncurry, which takes this kind of f and gives you back the other kind of f. Right? So in other words, right, you can say curry f applied to x and y, and then you can say uncurry g applied to x comma y. Okay? Cool. So this is the syntax. This means this, what you see here is function application through the context of what we have discussed so far. That is the function application. Expression applied to expression 1, further applied to expression 2, and so on and so forth up to expression n. Okay? That's essentially, E is expected to be a function of n arguments. All right? And in order for this to work, obviously, this E cannot be a number. Right? And this is why types are so essential at this point, because we would want E to have the right type of function from something to something else. And the first argument has to be of the type something, and the result is going to be of type something else. Okay? All right, more expressions. So this is a programming language made entirely of expressions. So we're going to have function definition. Everybody's familiar with what lambda is, right? Yes? Yes. Okay, cool. So instead of lambda, think fun, fun, which is fun to have, and it also again follows OCaml, I think. So we're going to deviate a little bit from OCaml in the way we specify the type. So we're going to write a curly brace. We're going to give the type of the function in there, right? After which we're going to enumerate the variables, the arguments to the function, right? The parameters to the function. So x1 up to xn have to be variables. Cannot be anything else but variables, right? And as we evaluate, we're going to expect them to be of types t1 up to tn. And then we write an arrow similar to OCaml, right? And then we can have any expression in which x1 up to xn may appear. They don't have to, but they may appear. Okay? Now, can other variables appear inside E? Yes, and we're going to have the concept of closures, right, where we include other variables, right, defined in higher scopes. All right, the variables x1 up to xn must be pairwise distinct. We can't use the same name for two different placeholders. The variables are essentially placeholders. They're like conduits, right, inputs into the code. And similarly, right, we can define recursive functions. And we're going to just do a trick here. We're going to say, we want to use the keyword rec_fun, all right? And we're going to add a variable which here appears as f. Okay? Now inside E, we expect all the x1 up to xn to appear. And also we expect the variable f to appear. All right? So this is sort of like writing, because we don't have yet the mechanism of defining something using the word equal, right? In let's say you're in what's a good language here? So the really good one would be Haskell, where you would write, for instance, factorial, and I'm just going to write f. Factorial of 0 equals 1, and factorial of n plus 1 equals n times factorial of n. And believe it or not, the definition, simple as it is, it works, right? And what's the important aspect here? I'm using this f both on the definition side and on the use side, right? This is the principle of recursion. All right? And now if you think very carefully about this is actually an equation. All right? So in math, you used to write something like x is equal to x square. I'm sorry, my handwriting is really very unpracticed, and x equals x square minus 4, let's say. Right? And this is an equation. You can find the value of x. Right? This is a very specific kind of equation. It's called a fixed point equation. And fixed point equations we can solve in algebra. We can solve them in an iterative way, right? So I will have the first bisector, and then let's say there's a curve. So this is a curve that will go something like this, and there's an intersection here, right? So the interesting thing is that I can pick an arbitrary value and then start doing this. Okay? Which means what? I pick up initial approximation x0, and then I compute a better approximation x0 equals f. Let's say this is f of x, and my actual generic equation is x equals f of x, right? F of x0, right? Then x2 equals f of x1. This ladder process means that, right? And I can keep going and going and going, and I'm going to get better approximations of everything, right? This is a fixed point equation. Guess what? The same principle works in programming languages. This is an equation or a system of equations where the unknown is f. It appears on both sides of the equality, right? And the important thing was that I have to be able to name the function to have recursion, right? Without having the ability to name the function, I can't have recursion. So this is what f is here, right? F becomes a name then that can be used inside here, and essentially now you have the f on both sides, right? There's an interesting problem here, because this f, what's the type of this f? And I'm jumping the gun a lot, but hopefully prepare you for the point when I'm really going to dump the definition on you, and in its formal way. And at that point, the surprise is going to be smaller. Right? So what's the type of f? You see, because it's an equation, this f is this thing. It's circular, right? The inside represents the full thing, right? So what's the type of f? So we know that the type of x1 is t1, right? The type of x2 is t2. The type of xn is tn, and this should be the result, which should be the type of e, right? This should be of type t. What's the type of f? Yes. So this whole thing is the type of f, and the type of the whole thing, because f is the whole thing, right? Cool? All right, so syntax is a bit weird, but, right, think of this as being f equals to, or in Python, if you like it better. So def f of x, right? And inside here, I can use f, right? This would be recursion. So it's the same thing. Cool. Same restriction. x1 up to xn have to be pairwise distinct, and f also has to be distinct from all the x1 up to xn. Cool? Everybody's happy? All right. So again, we're going to try to represent, or whenever we talk semantically about our expressions, we're going to ignore parentheses. We're going to assume that operators come in the right precedence, and we're going to have this writing. All right? We're not going to explicitly handle parentheses. It's a it's a complication that we don't want to deal with. All right? The arrow is right associative. So the arrow is just an operator at the level of the types, but it's just an operator, right? So whenever I have something like this, there have to be some brackets somewhere, right? So it has to associate. It associates to the right. Okay? And that's the right way. And you're going to see that's the right way when we deal with partial application. And actually, it's very easy to tell you why, right? So here let's say we have a function f, and normally we would say f1 and 2, and we would expect a result of type int. This is the result, right? 1 is of type int, 2 is of type int, right? So 1, 2, they're both of type int, and the result is expected to be of type int. But remember what we said about application. F is applied to 1, the result of that further applied to 2, right? And that should yield another result. So in principle, if I write this, I should still be okay, right? F is applied to 1, the result is further applied to 2, right? Yes? So what's the type of this? This now has to have a standalone type. What's the type of that? End to end, right? Which is this thing. So in other words, I take the f, I apply to the first int, and this is my result. Right? That's why the right association of the arrow is the right thing to do. All right? So, example, f, we want the type to be int int int, x2, another function, right? F int int, and y returns x plus y, right? So you take an integer, and that returns another function which takes another integer and returns an integer, right? So this is equivalent to saying int xy x plus y. Okay? And so there's no difference between the two. They're completely indistinguishable, right? Whatever set of values I apply to the first function and to the second function, they will always yield the same result. Okay? But this is correct syntax. So this overall expression has the type int to int to int. Takes two integers, returns an integer. Right? Now, since I am providing only one argument here, and since the arrow associates to the right, the return value of this function has to be this, right? Is that so? It is, because what I'm putting here, which is the result, has this type, which coincides with just this type. Right? Now, what you see in OCaml is that type is always inferred, so you don't have to always provide a type, and programs still are okay and compile, right? And it's very clear here that why do I have to write the same type twice? I'm writing this type here, and then I'm writing it again here. I shouldn't have to, right? So I should be able to allow types to be inferred. We're going to talk about type inference at some point. And type inference is a standard thing in functional programming. Now, let's look at a second example, which is more interesting, right? So now we're going to specifically use brackets to alter the precedence of the arrows. So I'm saying that this is a function whose first argument is, what's the first argument? What's the type of the first argument? It's a function, right? So this is the type of the first argument. I used brackets, and therefore that's my first argument. The type has to be a function. And let's call it f, and I want to return an integer, right? So let's call the argument f, and then what can I do with an f that is int to int? The only thing I can do is pass to it an integer, right? This is what's happening here. Okay, so I take in a function, and the only thing I can do inside is apply that function to an integer, and the result should be an integer, right? So this thing tells me that this thing is going to be an integer. Therefore, the result of the whole thing is going to be an integer. Okay? So you're seeing that these types are, essentially copied from one place to the other. The type here, because of the operation we're doing here, the type here and the type here have to be the same, right? And you're going to notice that certain types are impossible. I'm going to write down a type, arbitrary type, and I'm going to say, can you find a function that has that type, right? And you might not be able to, right? So not all types are reifiable. So, in the examples you're going to see a more comfortable syntax, right? That comfortable syntax, we don't want to accommodate it at the level of defining a semantics, right? So that's always a dichotomy. If I allow and whenever we deal in theory, we're always going to err on the side of removing of not making the language too rich, right? But I also want you to have the feeling that this is a realistic programming language, right? So what we're going to do is take some shortcuts, and you should know that these shortcuts are also taken by actual compilers and interpreters, right? There's a pre-processing step in many programming languages or in many compilers that take the full rich user language and strip it down to a core language, right? It's a bunch of very simple and straightforward translations and conversions, right, that remove the fluff, so to speak, right, and expose only the hardcore feature that have to be implemented and have to be dealt with seriously. So we're going to take a similar approach here, right? We're going to allow at the level of examples a lot of syntactic sugar, right? But much of that syntactic sugar will be swept under the carpet whenever we have to define the semantics of the language. So we're translating it away. That is typically done after type checking. All right, we're going to introduce all the syntactic sugar at the right time, and then not further mention it at the level of semantics. So, the one very important construct that is kind of pervasive, and it's becoming, it's moving into mainstream languages, right? The concept of a let. Anyone coding in JavaScript ES6? Yeah, right. So let is part of ES6 now. So we're distinguishing between constants and variables and scoped variables. So let allows the introduction of a scope. It is syntactic sugar, right? It is not an essential component. We can survive without it, albeit with more complicated syntax, less readable syntax. So let's put it right. So this let construct that says let this x1 have the value, e1, and we're going to have several such values being defined, x1 up to xn, in some expression, right? This is something that allows coders to make the code a lot more readable, right? You, instead of using x1 or x and y, you use meaningful names for these variables, right? And that documents the code, and also makes it have a more readable structure, right? But all this is translatable into this. We have a function applied to e1, e2, e1 up to en, right? And it's very obvious that this is correct, right? Because what are we doing? We are taking this e, and all occurrences of x1 up to xn inside here are coming from these definitions, right? x1 is e1, xn is en, so all occurrences of x1 up to xn in there are defined by the let bindings. We call these bindings. All right? So it's clear that the same thing happens here, because when I apply the function to its arguments e1 up to en, what's going to happen? e1 goes into x1, and so on and so forth. En goes into xn, and then as I'm going to evaluate e, the values of x1 up to xn inside e are going to have exactly the same values as in the let construct. Right? Clear? So this is syntactic sugar. Okay? Partially applied functions. So this is something that we were talking about previously. So you have a function that typically takes two arguments. We can take that function and convert it into two nested functions, each of them taking one argument. All right? And then whenever we have a smaller number of arguments, right? So let's say we have this f that takes 3 arguments. And then what happens if we only apply it to 2? Right? So whenever we have a fun f of some type, and I have x1, x2, x3, and expression e, right? As we seen before, we can translate this into fun f with some type x1, x2, and the result is another fun. This f is actually not here because it's not recursive, right? This is another fun with some type and takes x3 and it goes to the same e and end. Right? There's no difference. I can always take one function and break it into 2 nested functions. So one function on the outside and another one nested inside, taking the remaining arguments. So that works out of the box. And then if I do that, I don't have the problem of partial application at all. Right? All the functions are fully applied. So this is always fun to write. Syntactic sugar processors. There are languages that allow the the syntactic analyzer to be modified on the fly. Actually, OCaml is one such language, and I think one of your projects is going to use that. Right, so you can add syntactic sugar features to your language as you please. It cannot, as the program executes, you can hook new syntactic sugar hooks inside your syntax analyzer, and then below that point you can start using your new syntax. And it's an essential way of defining domain-specific languages, DSLs. How is this translation going to be performed? We have a syntactic tree, right? A syntax tree, and this is represented by the operators. So we're going to have a big match, right? And we're going to try to detect the places where syntactic sugar may be used. So this is one place, right? And then what am I going to do here is I'm going to produce the expression, the structure, the syntax tree that corresponds to that translation. Okay? All right. So this is another example using let. Okay. So we're using about pi, which is an approximation of pi. We're defining a function called square. That squares a number, and we want an expression that is 4 times about pi times the square of 6,371. All right. So this would be the syntax sugar removal of that expression. Okay. So let's see what's going on here. Right. So we have two variables, about pi and square. Square is a function. So what we're going to do is take this expression and put it inside a function, and the arguments are going to be these and this, right? Pi and square, and this goes here. I'm not going to copy it, and this entire thing is going to be applied to what? To this, and then this entire thing, right? This is going to go here. So let's put them as small boxes, and this entire thing is going to be my expression, right? So this box, whenever this function is evaluated, this box is going to become the value of about pi, and this other box is going to become the value of square. And whenever whatever is in here is evaluated, about pi has the right value and square has the right value. Okay, so this is what's happening here, and we can verify that that translation is very mechanical, right? So it is something that a machine can do very well. Is this clear? Everybody's happy? Cool. Let's look at recursion a little bit. So one way to compute power, the power of a number raised to another number, right? How do we do that, right? We take the two numbers, and if the exponent is 0, then the result is 1. Otherwise, we multiply x with the recursively applied power of x and y minus 1. Okay? And you're going to say now, how come I don't use brackets here? Right? That's because that's how the syntax analyzer in this language works. It's probably the way your labs are working as well. Right? So y minus 1 has higher precedence than the invisible operator of application that sits right there. Okay? Anybody has doubts about this? It's a bit weird as a syntax, but I think it's pretty clear. Right? So notice the fact that we can use in this syntax, we're essentially saying that power is the name of this whole thing. And I can use it in here. Okay? The type of this entire thing is this. And it's recursive now, right? So whenever I reuse it, I have to conform to this type. So I have to pass to it 2 integers. All right? So the type has to close somehow. I'm assuming it to be here, but when I'm using it again, I have to use the same thing. So by the way, before we do that, is recursion really necessary? So let's say I have a language without while loops, which is what we have now. Is recursion really necessary? Is there another way to compute the power, or let's say factorial, that doesn't use recursion at all? Yes, no, maybe? What do you think? How many think yes? It's possible to compute without recursion. Some people say yes, they nod. I'm going to ask you how. Louder. No, without. We haven't defined one, and let's say I don't allow you to define. So let's say I don't allow you to define while loops, I don't allow you to define variables. I don't allow you, so all you have is, I don't allow you to have assignment at all. All you have is if, and all the expressions, of course, and functions, lambdas, not functions, lambdas. Can we make do with those? Can we compute factorial? Some say yes, some say no. What is it? Again? No, there's no power operator. So JavaScript or Python, what do you want? I'm already in JavaScript, right? So let's say I'm gonna say function, and I'm not allowed to give any names, right? No assignment. So I am going to play a trick. I'm going to take in an f and an n. I want to compute factorial, right? And I'm going to say if n is 0, return 1, else return, what do you think I should put here? All right. And now I have this function. I have to apply it to something. What do I apply it to? Let's say I want to compute factorial of 10. So obviously, what I'm expecting in here is an f and an n, right? So the second argument is going to be my number, 10. What should be the first number, the first argument? All right, so I'm going to take this up to here, right? Again? N is supposed to decrement. Good point. Very good point. So at least that part you got. Very good. So I'm going to take this thing, and what do you think I'm going to do it? I'm going to do with it? See, this is a function that expects an f. In here, the first argument is to be an f. Where do I get an f from? I just highlighted it, right? So I'm going to take it and copy it here. And then evaluate this. And get 1. Why? Oh, I have to multiply with n, of course. N times, right? Not in the best of my capacities, right? So, it's possible to not use recursion, right? So this looks like a mind trick. It's not, right? So it's possible to survive without using recursion. You can play this in any language, what I've just done. What's the disadvantage? You duplicate code, right? You have to take the same. Imagine that your expression is like, your function is 100 lines long, right? Or maybe 20 lines long. Are you going to duplicate those 20 lines? Not such a good idea, right? So recursion, in essence, is syntactic sugar, right? It is very possible to survive without it. And then remember this trick when we're going to define the semantics. Okay? Everybody understands why this works? Cool. So this is a recursive method. Everybody, I'm hoping, understands. Let's define one that has a higher order function, right? So you see here we have 4 arguments. The third one, the one in here, is another function. Okay? So this is sorry. So this is a function similar to fold, which we're going to, or maybe you know it already, it's a higher order function, right? So the important thing here is that it takes a argument, it takes an operator, right, which is this guy, and then it performs the operation between this and the recursive application where we have decremented the argument by 1, right? So for instance, if this operator would be multiplication, which is something of this type, right, you could compute the factorial. So if we apply this function to what? xy. Oh, no, we could compute the power, right? We could compute the power. So power would be defined as what? As, let's say I want to compute the power of 10 to 20. So I would have 10, 20. I would have fun, and I would have some type here, x, y, return x times y, and 1, right? So this is something raised to the power of 0. So if I would put this in, I would obtain exactly the power operator that we have written on the previous slide. And notice how this operator is now made generic. So what I need to pass as the third argument is another function. Cool? Cool. You're going to see a definition like this in your lab. So how do we define an abstract syntax tree? Well, we have to encode all the expressions. I'm sorry. I'm not really feeling that well. So you have to define an expression of every every type, right? So if you have a Boolean, a Boolean constant, you have to essentially tag, right? So you're going to think that your abstract tree is a box, and then inside here there are other boxes, right? But typically we don't look at them as being boxes inside. We draw arrow and we draw the boxes separately, because what we would store in these small placeholders here is actually references, right? So it works like this. So every box must have a tag and must contain the subcomponents which represent the sub-expressions, right? So we're going to always have, oh, this is the tag, and this is the contents, right? I'm going to have a tag of bool const, and the contents of that tagged box is one Boolean value, right? Or I'm going to have an int const tag and one value of type integer. Or I'm going to have a var tag, and this is a type that represents identifiers, and that should typically be a string, but maybe it's a more restricted form of string. Unary primitive application, which would be an operator identifier. So this is the tag, and then these guys can be unary minus or a negation, right? And then we would have another expression now. So recursively, we can have other expressions. Binary primitive application, again here, and we have an operation identifier. This can be plus, minus, multiplication, division. So op_id is probably a string, and then you would have two expressions, because the binary operation is between two expressions, right? And this guy has the same type as this guy recursively, right? Because it's a tree. So remember that trees have recursive elements, right? It's either a node of two other trees or a leaf of something that is sort of like a constant, right? So these two guys are, or these three guys are the leaves, and everything else is the nodes, right? The nodes have different tags. So the syntax analyzer that you have in the lab will take the string, right? This comes from the input as a string, comes from a file, right? The file is read, appears in memory as a string, goes through the parser or syntax analyzer, and you get something like this, right? An element of the type SPL expression, right? Which has a top level operator and then has sub-expressions, right? And effectively is a tree. This is what we call it, a syntax tree. Okay? It is called an abstract syntax tree because it doesn't contain all the elements from the original string. The actual there exists an actual syntax tree. So if you learn parsing, right, there are several types of parsing trees. The end product of it is the abstract syntax tree, which is the easiest to process. And actually, I'm going to skip telling you what the others are because we don't have a lot of time. So I don't think I want to start dynamic semantics right now, given that it's very close to the end of the class and I haven't given you a break. But we're going to essentially follow the same steps, right? So dynamic semantics, we're going to talk about contraction. One interesting aspect here is free variables, and I want you to think about this, and so I'm going to try to give you a hint at what's going to come next time, right? When we do the dynamic semantics, we're going to go from the large expression, right, to smaller and smaller and smaller expressions, right? The way we did for expressions. Now, when I am going to do that with a function, x1 up to xn, and there's some type here, right? And I'm going to have an e. So when I'm going from the end, there's no bracket here, right? So when I'm going to go from this level one level down, this is the one level down, right? So when I look at that E in isolation, x1 up to xn appear without a definition. That can cause a problem, right? Because whenever we execute a program, all variables are what we say is bound. There is a place of definition that tells us how to get a value for that, right? But we're breaking this uniformity, this rule, as we go from a bigger level into a smaller level, right? I want to define my semantics, and as I go from the big level to the small level, I'm going to see this E and the x1 up to xn appearing to be undefined, used before they have been defined. How do we solve that problem? Okay? So that will be solved with a notion of called the environment, which keeps track of undefined variables and tries to, as we go back to the bigger level, to the upper level, tries to match every undefined variable with a definition, so that in the end no variable is left unmatched. Is everybody happy? Questions? Cool. See you next time.